Good morning, all of you. Sairam. Children, in the previous class, we all have learnt about the Rawls law. And I have told you that today we have to start with the types of solutions on the basis of Rawls law. Children, let us first quickly revise what was Rawls law. I have told you, according to Rawls law, in a solution, the partial vapor pressure of each component is directly proportional to the vapor pressure of that component in the pure state into its mole fraction. Simply, you can say the partial vapor pressure is directly proportional to the mole fraction. Removing the sign of proportionality, a constant comes. That constant is equal to the partial pressure of that component in the pure state. So, you all can say P is equal to P naught into zeta. That means P is the partial vapor pressure, P naught is the pure state vapor pressure, and zeta is the mole fraction. Now, today's class will be starting with the types of solutions on the basis of Rawls law. On the basis of Rawls law, there are two types of solutions, ideal solutions and non-ideal solutions. Now, first of all, we have to start with the ideal solution. An ideal solution is that which obeys Rawls law. That means which obeys the equation PA is equals to P naught A into zeta A. So, according to Rawls law, an ideal solution is that which obeys the equation PA is equals to P naught A zeta A. Similarly, for the other component, if it is volatile, it will obey the equation PB is equals to P naught B zeta B. Now, children, it obeys the Rawls law over the entire range of concentration. Entire range of concentration means whatever be the quantity of solute added to the solvent, but still it will obey the Rawls law. Now children, you all can see a graph which is being displayed on the screen. Now, according to that graph, if we see here you all can see on the left hand side, that is on this axis. On this axis, you all can see it is the vapor pressure, and down here it is the mole fraction. Now see, if suppose the mole fraction of component B is 0, this component B is 0, that means component A is present in the pure state. In the pure state, the vapor pressure of component A is equals to P naught A. Now, if we increase the mole fraction, we are moving to this side now. If we increase the mole fraction of component B, and ultimately we reach the component B mole fraction become 1 and that of A becomes 0. In that case, you all can say component B is present in the pure state. Then the vapor pressure of component B will be equal to P naught B. Now, this graph, it tells you that this line corresponds for PA. PA is equals to P naught A into zeta A. Similarly, the other line, this line, it corresponds for PB. You all know PB is equals to P naught B into zeta B. This line corresponds for PB, and this line is the total vapor pressure of the solution. Now, the total vapor pressure of the solution is PS. This line corresponds for PS, which is equals to PA and PB. So, you all can now say that the total vapor pressure of the solution will be part of it will be because of component A and a part will be of component B. Now, the contribution of component A in the vapor pressure was equal to P naught A zeta A, and that of component B was equal to P naught B zeta B. So this is your Rawls law and this is your ideal solution on the basis of Rawls law. Now I hope you all must have understood. Now children, next we have to proceed with the characteristics of ideal solution. Now see, ideal solution is made only when the force of interaction between the solute and the solvent are of equivalent, you can say, energy. That means when the force of attraction between AA will break and BB will also break, they will form a new force of attraction between A and B, and that should be of the same energy, the same magnitude as it was there in case of AA and BB, that is solvent and solute. In that case, neither energy will be released out nor energy will be consumed when the bond will break and the new bond will form. That means delta H of mixing, that means the enthalpy change on mixing will be 0. That is your second characteristic. I'm sorry. Now, see, the first characteristic was the force of attraction between AA and BB is equals to AB. And when the force of attractions are equal, that means when the bonds will break and new bond will form, the energy consumption will be equal. Neither energy will be required nor it will be evolved out. So, delta H of mixing, the enthalpy change of mixing is 0. Now, for such a solution, when we mix the two, the solute and the solvent, when they are mixed together, neither volume will increase nor volume will decrease. Like for example, if we have 20 ml of solvent and 10 ml of solute, then when the two are mixed together, the total volume of the solution will remain 30. But in the other case, if it is not an ideal solution, it will not be 30. It will either be less than that or it will be more than that. Now, an example of an ideal solution is N-hexane and N-heptane. Similarly, another example is benzene and toluene. The next example can be chlorobenzene and bromobenzene. When the bonds are breaking, new bonds are forming, then energy change is not taking place in such cases. So, such solutions are called the ideal solutions. Hope you all must have understood. Now, the next type of solution on the basis of the Rawls law are the non-ideal solutions. Now children, non-ideal solutions are those solutions which do not obey Rawls law over the entire range of concentration. Now when do they obey, that we will discuss later on. Now Rawls law, they do not obey, that means for them this PA is not equal to P naught A zeta A and PB is not equal to P naught B zeta B. Whereas for ideal solutions, PA was equal to P naught A zeta A, PB was equal to P naught B zeta B. For non-ideal solutions, PA is not equal to P naught A zeta A and PB is not equal to P naught B zeta B. Now children, non-ideal solutions are further of two types. The first type is the non-ideal solution showing positive deviation from Rawls law. And the second is the non-ideal solution showing negative deviation from the Rawls law. That means if we see that here PA is not equal to P naught A zeta A and PB is not equal to P naught B zeta B. Not equal to means it can either be greater than or it can also be less than. Now on the basis of that, there are two types of non-ideal solutions. The one in which it is greater than and the other one in which it is less than. Now coming to a solution, non-ideal solution showing positive deviation. In case of positive deviation, PA, that means the partial vapor pressure of the component A in the solution is greater than that of its pure component and its mole fraction. Similarly, PB is greater than P naught B zeta B. Now children, when does this thing happens? It happens only when the force of attraction between component AA and component BB are not equal. Now children, for such solutions, when component A and component B are mixed together, then the volume also changes. Like for example, suppose we have 20 ml of the solvent and 10 ml of the solute. When the two are mixed together, then the total volume of the solution will not be equal to 30 ml. For positive deviation, it will be greater than 30 ml. For negative deviation, it will be less than 30 ml. Clear? Similarly, when the two are mixed together, either the reaction, the dissolution process will be endothermic. In case of positive deviation, it will be endothermic. In case of negative deviation, it will be exothermic. Now coming to the characteristics of non-ideal solutions showing positive deviation. Now children, as I told you, non-ideal solutions are those for which PA is not equal to P naught A zeta A, PB is not equal to P naught B zeta B, and for non-ideal solution showing positive deviation, PA is greater than means positive, and PA is greater than P naught A zeta A. Similarly, PB will be greater than P naught B zeta B. Now, for such solutions, the force of attraction between the solute and the solvent will be less than the pure solute and pure solvent. When the bond was there between pure component AA and pure component BB, and when the two bonds are breaking, the new bond is formed between A and B, then the forces will be less. Similarly, delta H of mixing will be positive for positive deviation. That means the enthalpy change on mixing is positive, that is the dissolution process will require some energy, and with the increase in energy, dissolution will also increase. Similarly, delta V of mixing is also positive. Here it should be V. This delta V of mixing should be positive. That means the volume change on mixing should be positive. Volume will increase. The total volume, if 20 ml and 10 ml are mixed together, the total volume will not be 30 ml. It will be more than 30 ml. It will be either 31, 32 or point something. Clear? Now, coming to the non-ideal solution showing negative deviation. Now children, a non-ideal solution showing negative deviation will have PA less than P naught A zeta A, PB less than P naught B, this should be B, P naught B zeta B. Now, for such solutions, the force of attraction between the solute and the solvent will be stronger. That means solute and solvent, they will be binding through a stronger force of attraction. So, the resultant vapor pressure will be less. More energy will be required to contribute to the vapor pressure. Now, for such solutions, the dissolution process is exothermic. That means some of the energy will come out when the solute and the solvent are mixed together. Delta H of mixing is negative, that is exothermic, and the volume change will be negative. It should be V here. This is V. Now, volume change will be negative, that is delta V of mixing. That means if we mix 20 ml of the solvent and 10 ml of the solute, the two will mix together and the total volume of the solution will not be 30 ml. It will be less than 30 ml. It will be either 28, 29 or point something. Is that clear? Now, coming to the examples of non-ideal solution showing positive and negative deviation. Now, an example of a non-ideal solution showing positive deviation is ethyl alcohol and cyclohexane. Similarly, now see children, what actually happens when ethyl alcohol was present alone. Two molecules of ethyl alcohol were joined together with a hydrogen bond. You all know ethyl alcohol has got an oxygen and that oxygen is joined with a hydrogen. That will form one ethyl alcohol molecule will form a hydrogen bond with another ethyl alcohol molecule. Now, if suppose cyclohexane is mixed into it, then the two will get mixed together and the hydrogen bonds between the ethyl alcohol molecule will break, but the new bond formed between cyclohexane and ethyl alcohol will not be of such strong magnitude as it was in case of ethyl alcohol alone. So, such a solution will show a positive deviation from Raoult's law, and for such solution the dissolution process will be endothermic. More amount of energy will be required to dissolve cyclohexane into ethyl alcohol. Now, coming to the non-ideal solution showing negative deviation. Now, in negative deviation, if we see an example of a non-ideal solution which is showing a negative deviation is acetone and chloroform. Now, acetone and chloroform, when the two are present separately, then the force of attraction between the two is of low magnitude, but when the two are mixed together they will form hydrogen bond, one acetone molecule and one chloroform molecule. The two will form a hydrogen bond, so the force of attraction between A and B will be of higher magnitude, and if they are of higher magnitude, that means energy will be released when the dissolution process is taking place. Now children, you all, I think, are now clear with ideal solutions and non-ideal solution. As I have told you, let us quickly revise what we have learned today. Ideal solutions are those which obey Raoult's law. That means PA is equal to P naught A zeta A and PB is equal to P naught B zeta B. Characteristics of ideal solution we have learned today is force of attraction between AA and BB is equal to AB. Second characteristic, delta H of mixing 0, delta V of mixing 0. One example you have to learn, at least many examples are there, but one you should be knowing, that is N-hexane and N-heptane. Now coming to non-ideal solution. On the basis of Raoult's law, the other type of solution is non-ideal. A non-ideal solution is that which does not obey Raoult's law over the entire range of concentration. Now, for non-ideal solutions, PA is not equal to P naught A zeta A and PB is not equal to P naught B zeta B. And the two types of non-ideal solution, positive and negative, their characteristics also we have learned today. Now, we have completed with today's topic. I am giving some of the questions as home assignment. You all are requested to kindly solve those questions at home, and will proceed further in the next video with the next topic. Thank you. Sai Ram.